We're talking about applications of perturbation theory. The first attempt was, we had a perturbing term, your h hat dashed, the addition to the Hamiltonian was proportional to x to the fourth, so we just plugged that into the formula and derived a correction, first order correction to the energy eigenvalues. Well, we will do 1, 2, 3 more before we get into a slightly new topic, a second major approach when you're approximating, when you don't have exact solutions. And that second major approach be in the fourth session on this board, called the variational method, but that's a few sessions away. Right, so the second one is called the electric polarizability of the hydrogen atom. So you're asked to, so you apply an electric field, E, to the hydrogen atom, and you're told that the hydrogen atom is in the ground state, so it's at that lowest energy state. And you may remember from discussion on the hydrogen atom earlier lectures, that the ground state is symmetric. It's a so-called S wave. S, I assume, stands for symmetric. Alright, so, and you're asked to find the energy correction to second order, not first order, second order. So you ask for E2. So you get that from expanding out the energy corrections to second order, lambda squared. So you look at the coefficient of lambda squared. Okay? Now the reason why you need to do it to second order is it works out, and I'll do it in a moment, that the correction to first order is in fact no correction because it's 0. So E1 is 0. So well, let's show that to start with, right? Okay, so the ground state's spherically symmetric. There's S wave. The wave function is spherically symmetric about the nucleus, right? So we're free to choose any any axis we like. So let's just arbitrarily choose one of them to be the z-axis, and then we did this from the previous session. So h bar, the perturbing Hamiltonian, so it will be of this form. So that's your force. E is the charge on the electron. E is the electric field that you're given. And Z, to make it a unit of work. Potential energy is like force times distance. Talked about that a bit before. Okay, so that's the perturbing Hamiltonian. You plug it into your first order correction term, which we've done before. Okay, so U naught H hat dashed U naught. This should be a conjugating term here, but right. So this times this is just effectively this squared. So that's an even function. Okay. And h, because of the z here, is an odd function, so the whole thing is so this integrand is an odd function, and it's over the volume, so the odd function over the whole volume, that will be 0, right? Because of the integrand is odd. Okay, so we need to go to second order. Now from the theory, now by the way, there was an inconsistency, an error in the textbook that I noticed. Earlier when we put this formula on the board, for the second order correction of the energy eigenvalue, so E2, this division mark was not in the text. Now I haven't actually derived it, so I'm just signaling you that there's an inconsistency in the text. You need to check Probably this bar here should be there, but it was not the first time we came across it. You know, this formula in the text. So just a minute. The light. I don't know. The cloud's gone over. It's got dark. I'll switch on the light and I'll put on my cap. Just a minute. I hope that helps. Right. Okay, so to find the second order correction, so E2, we've had this formula before. Okay, now we're talking about the ground state, so your n will be 0. Okay, so E0, and so this will be 0. So here, and the n here will be 0. Hence this. Okay. So this is your, what do we call it? It's obviously a matrix, perturbation matrix. Okay, so this to first order. Right, so sum of, so m is not equal to n, so m is not equal to 0 because ground state. So we've got this sort of thing. Right? Now this summing this, it's a sum, so summing this is complicated, according to the text. And then there's a bit of a remark here analogous to classical mechanics, so a bit of a footnote. So the real work continues from here onwards. But anyway, notice if you look at this formula, the shift in the energy is proportional to E squared, the big E, the electric field, vector field that's applied, E. Right? So the energy correction E2, so E's here, E energy and the E here, don't confuse them. The E here is the electric field, right? And the energy shift E2 is proportional to the square of the electric, strength of the electric field, E. Right? Which is what's being said here. And if you're thinking classically, if you had a system with polarizability alpha, so you could polarize it, so meaning one pole, we'll say north pole, you had more positive charge, and the south pole had more negative charge, so your entity, whatever it was polarized, and you can measure that by alpha. This is not proportional sign, just the polarizability. Okay? In that case, then the potential energy is of this form. That's from classical mechanics. All right. Now, when you're talking about the ground state energy, your wave function is symmetric, spherically symmetric. So the polarizability is 0. Right? There's no concentration of charge one end and lacking negative charge at the other end. There's no pole. There's no polarizing at all. But when your hydrogen atom gets excited, so the excited states of the hydrogen atom, then you can get polarizability. Intuitively, if you think back to your polar diagrams, remember we're drawing the diagram, the probability densities for the hydrogen atom at in excited states, above ground. The ground state, above the minimum energy level, and we've got these sort of wings and lobes, remember? So intuitively it makes sense that excited states of the hydrogen atom would be polarizable. So that would be consistent with your E2 here. Okay. Right. Now, okay, back to the math. Now, we don't have to sum. In this particular case, we don't need to work this out. This complicated sum of all these terms. There's a trickier, easier way, and it results from the fact that the first order correction E1 is 0. Okay. Now, from the theory of perturbation theory, we've had this before. You've seen this before. This equation. And it's important, so I've labelled it, so I just call it star circle, the usual thing. okay, to label this equation. So we can actually use this to solve for E2 with an intermediate step, and that'll become clear in a minute. Okay, so we're going to use this, right? Now, in this particular case, excited state of the hydrogen atom, E1 is 0. So this left-hand side here just drops out. Okay, now that simplifies things a lot, because then, see, we know this. The perturbing term we know. It's just this, right? Minus E big EZ. So we know that. We know the ground state. We know these, and so we can solve for this. And then this is the intermediate step. So if we know what the first order correction to the eigenfunctions, U1, if we know what that is, we can then use that in a formula for E2, which will be at the beginning of the next session. But anyway, I'm just sort of giving you the general direction. Okay, so for the hydrogen atom, U1 is 0, so this left-hand side drops out. So we can find an expression of U1 in terms of U0, right? So we don't need to use this complicated weighted sum expression to find E1 in terms of E0s. We don't need to use that, right? Okay, so this here, this right hand side here, is equal to 0. So let's actually write out the equation. So this, the U1, the U1 term, this is this. Okay, we're talking the hydrogen atom. So H0, Hamiltonian, is the del squared term. Here's your potential, Coulomb potential, something over R. This is your ground state energy E0. Right now. So I guess n is 0, right? So here's your E0 of 0, that's your eigenvalue. Your U1, here it is here, and H dash, the perturbing potential, is just this, right? And this whole thing is 0, so you plug it into 0, and then, so this gives an expression for UN1. And I'll, next session, give you a formula that allows you to derive E2, the second order correction of the eigenenergies, the eigenvalues for energy, in terms of this U1. And hence we can find E2. And that would be then the end of the discussion on the second application of perturbation theory. So I'll just move straight on in the next session, continuing on from here.